Assalamualaikum. Today we will present the topic of gamma radiography for non-destructive tests. At first, let me introduce our team members. I'm Nurul Ain Salwani and we have Nur Yasmin Shuhada, Nur Rashika, Balkis Sufia and Aina Aimani. Today, we will explain about gamma radiography for non-destructive tests. To start with, what is gamma ray? Gamma rays are the highest energy electromagnetic wave produced by radioactive substance. We choose these topics because it plays a significant role in modern physics, astrophysics, medicine and technology. Studying gamma ray helps students understand the structure of atoms, the behavior of matter under extreme conditions, and the nature of the universe. Method of the study that we use is lecture note, scientific journal, education website, and research articles. Also, while we study this case, we face the challenges, which are difficult to understand, complex scientific terms, and advanced physics concepts related to radiation and nuclear processes. Another is trustworthy sources among the larger amount of information available online. To overcome this problem, we read material that were easier to understand and reliable sources.
This slide shows the main modern physics concept involved in gamma radiography. First is radioactive decay. Radioactive decay is the spontaneous transformation of an unstable atomic nucleus into a more stable nucleus while releasing radiation, which is gamma radiation. In gamma radiography, radioactive sources such as iridium-192 or cobalt-60 undergo radioactive decay and emit gamma rays. These gamma rays are the source of radiation used to inspect metal structures and welds without damaging them. Second is the interaction of gamma rays with matter. When gamma rays pass through a material, they interact through processes such as the photoelectric effect, Compton scattering, and pair production. This interaction determines how much radiation reaches the detector. Areas with defects, cracks, or voids allow different amounts of radiation to pass through, creating contrast in the radiographic image. There is attenuation of gamma rays. Attenuation means the reduction in gamma rays intensity as radiation passes through a material due to absorption and scattering. Thick or dense material absorbs more radiation, while thinner regions absorb less. This difference helps inspectors identify internal flaws and variation in material thickness. Finally, gamma emission refers to the release of high-energy electromagnetic wave from radioactive nuclei. Gamma rays have very short wavelength and high penetrating power, allowing them to pass through thick steel components. Because of this property, gamma radiography can be used to inspect pipelines, pressure vessels, and welded joints. These slides present the modern physics law and theories that form the foundation of gamma radiography. First, the exponential attenuation law. This law states that the intensity of gamma radiation decreases exponentially as it passes through a material. This law is important because thicker or denser material absorbs more gamma rays, allowing defect and variation inside a component to be detected. Next is nuclear theory, which explains the structure and behavior of atomic nuclei. According to this theory, unstable nuclei undergo radioactive decay to become more stable. During this process, gamma radiation can be emitted. Radioactive isotopes such as iridium-192 and cobalt-60 are used in gamma radiography because they continuously produce gamma rays for inspection purposes. Finally, quantum theory explains that electromagnetic radiation exists as discrete packets of energy called photons. Gamma rays are high-energy photons. Their interaction with matter through processes such as the photoelectric effect, Compton scattering, and pair production determines how much radiation reaches the detector and forms the radiographic image. Overall, the effectiveness of gamma radiography relies on the combined principle of radioactive decay, gamma emission, interaction with matter, attenuation, nuclear theory, quantum theory, and the exponential attenuation law. These modern physics principles allow engineers to inspect the internal condition of materials safely, accurately, and non-destructively.
Next, I will move on with the gamma ray application in daily life. So first of all, we have oil and gas pipelines. So gamma ray is used to shoot radiation through welded joints on cross-country pipelines. For example, we use gamma ray to detect the internal air bubbles, crack or slight intrusions. Secondly, we use gamma ray for aerospace maintenance. This is used to scan the critical airplane parts like engine turbine blades and landing gear. This is used to find the deep internal cracks or hidden corrosion. So last but not least, we have civil infrastructure. Gamma ray is used to look inside reinforced concrete structure. It will map out the hidden rear structure and identify structural voids. Moving on is the gamma ray challenges. So first of all, we have radiation hazard. So technician will face elevated risk of accidental exposure. For example, if a radioactive isotope gets stuck outside its protective safety shield, it can cause severe radiation burn or fatal doses. Second, we have national security threats. Materials like cobalt-60 and iridium-192 are under strict international tracking. This tracking is necessary because they could be stolen or lost or build a radiological bomb. Last but not least, we have continuous decay and logistics. Gamma sources constantly weaken and cannot be turned off. They require an expensive or never-ending cycle of replacement and hazardous waste of disposal.
Gamma ray radiography offers various career opportunities in the field of non-destructive testing or NDT. A person usually starts as an NDT radiography technician where they assist in carrying out inspections and handling radiographic equipment. With more experience and certification, they can progress to become an NDT inspector and eventually a level 3 specialist who is responsible for developing procedures and supervising inspection activities. These professionals are needed in industries such as oil and gas, aerospace, and construction because safety and structural integrity are very important in these sectors. To succeed in this career, a strong understanding of radiation physics is necessary. Professionals must also follow strict safety regulations because they work with radioactive sources. In addition, obtaining recognized certification is important to prove competency and ensure safe working practices. Self-development in gamma ray radiography begins with learning the basic principles of radiation and how gamma rays are used for industrial inspection. This knowledge provides the foundation for understanding image formation, defect detection, and radiation safety. After gaining the theoretical knowledge, professionals typically pursue certifications such as ASNT Level 1 and Level 2. These certifications help validate their skills and allow them to take on greater responsibilities. Practical experience is equally important. Through industrial training, internships, and hands-on inspection work, individuals can improve their technical abilities and learn how to interpret radiographic images accurately. Experience with other NDT methods can also broaden their expertise. As they advance in their careers, their goals may include designing inspection procedure, leading inspection teams, and ensuring that all work complies with safety and quality standards. These responsibilities require both technical expertise and strong leadership skills.
Now we will look at the significance of self-development. First, the landscape of radiography is shifting rapidly toward the advanced digital imaging and automation. If we don't commit to ongoing learning, we cannot leverage this tool for the speed and the precision that modern projects demand. Second, we must stay updated on radiation safety regulation. These standards are dynamic, and continuous training is the only way to ensure that we remain full compliance with the latest safety procedure to protect ourselves and the public. Third, and perhaps the most critical, is the improvement of inspection accuracy and reliability. By refining our technical knowledge, we become better at identifying subtle defects. This directly reduces the risk of missed failure, ensuring the highest quality of the industrial structure that we inspect. However, this professional journey is not without its hurdle. As you can see, there are 4 challenges, and addressing them require a proactive strategy. First, we manage radiation exposure risk by creating a LARA principle, keeping exposure as low as reasonably achievable as a core discipline, not just as a guideline. Second, to combat rapid technology changes, we move beyond basic proficiency by actively attending specialized workshop and vendor training. Third, we view certification requirement not as administrative burden but as essential benchmark. Obtaining higher level NDT certification is how we validate our competence to our peers and clients. Finally, we address the immense responsibility of defect detection by ensuring that every inspection is backed by continuous hands-on field experience. We don't just learn by theory, we apply it to sharpen our judgment and learn from every test we perform.